morning, everyone. I've spoken with many of you already this morning and yesterday, but I'm Jeff Alstott, and I'm at IARPA. Before I talk about IARPA, I'll talk about DARPA, which it's been around for 50-odd years. It does high-risk, high-reward research for the Department of Defense, and so it's created such things as stealth technology, GPS, and a little something called the Internet. So DARPA has been of great value for society. I don't work at DARPA, I work at IARPA, which is sort of the intelligence community's ARPA. So we also fund high-risk, high-reward research, and we've only been around for about 10 years. We were created after 9/11 in one of these integrating measures, adding a new layer in order to help the intelligence community coordinate. So we have not yet created the internet. We're working on it. So we've funded work about forecasting techniques, cryptography, of course, quantum computing. We've had a Nobel laureate funded by IARPA, then go on to win a Nobel. And our customer is the intelligence community. So I'm going to start by asking you some questions, and then we can talk about some research directions. So the question for the audience today is, what's the point of science? So this is a work colloquium on visualizing and modeling science and technology. Does anyone have their favorite theory of what's the point of science? Knowledge creation? All right, so just on, is it papers? That's the first question. Not, right, okay, great.
Societal transformation.
Societal transformation, okay. Knowledge, so I would have agreed with Cesar. It's about figuring things out about the world, or in different nomenclature might be making models of the world. So similarly, what's the point of technology? Is it patents? Is it making patents? No. Sure, I would say making things in the world, or making capabilities, is what you just said. So a question one might reasonably ask if one is funding research in this direction is, why are we studying papers and patents? Right? And it's not because we're bad people or we don't understand what it is that science and technology actually are. It's because that's the data that we have, right? We can study papers and patents because, thanks to the efforts of careers of spanning decades, many people in this room, we have data that we're able to study from papers and patents. But the data that we've been analyzing and the capabilities or the knowledge that we've been developing, will it help us answer a question like this? When will we understand what schizophrenia is and what causes it? Right? So currently, if you want to answer this question today, which people in the US government and other governments around the world who fund research, be that in the NIH or elsewhere, foundations or whatnot, they need to know the answer to this kind of question in order to decide what to do. And we as scientists need to have this sort of thought process in our head when we're deciding what research we want to do or what capabilities we want to develop. So how do we answer this question? Or even a simpler question, much simpler, where the object of interest is clearly defined. What will be the weight of a 4G radio in 10 years? So we've developed a lot of understanding of how science and technology evolve, but what is our level of understanding with being able to address this question? Or, for other people in the room, if we train X more graduate students, how much quicker will we understand what schizophrenia is and what causes it? Or, if we subsidize private R&D by X% more, what will then be the weight of a 4G radio in 10 years? So these are the policy questions. These are the things that I think many of us as scientists are trying to figure out for our customers, where our customers could be companies or governments or just society, right? These are the sorts of critical pieces of information that we would really love to be able to develop in order to help society function in all sorts of ways. But these are really hard questions which is why we haven't been running right at them, because we're not fools. But part of the reason that they've been so hard is that we don't have the right data. As we said, the reason that we're studying papers and patents is because that's what we have data on, which is absolutely understandable and commendable. So at IARPA, we fund high-risk, high-reward research, and so we try to make investments that will change the game of what people are doing research on. So I'm going to talk briefly about a specific research vision, and then we can discuss technical details, et cetera, either in Q&A or later. So let's focus on technology for now. So we've said that in technology, a lot of folks, including myself, have studied patents in depth because that's the data that is available. But what we really might want in order to be able to answer questions like what a future technological capability would be is that we want historical data on technology performance over time. So you might want to have piles of data or have collected data that looks something like this. So let me just explain what you're seeing here because it's a mess. On the left here, we have many different kinds of technology for storing energy. And so we've got on the y-axis here the energy density. So this is watt-hours per kilogram. And then we have time on the x-axis, and we can see in the legend all these different forms of batteries or capacitors or flywheels or whatnot, and their performance over time. And then we can see the different evolution in these different technological domains. And then on the right, we have something that many of us are much more familiar with, which is Moore's law and its extensions. So we have millions of instructions per second across time, and we have all these different substrates by which we have done computation, including what we think of as Moore's law, but also different technologies before then, which included manual calculation by hand. So in order to develop theories of how this stuff evolves, including things like what R&D funding would be needed or how many graduate students would be needed in order to manipulate this, you need to have this data, right? In order to build such a theory that's data-driven, you first have to have data that looks like this. And unfortunately, this data is very precious, and we have very little of it. And the state of the art right now is on the order of 100 good time series. What exactly is a time series can get a little murky, but you know, something on the order of a few hundred. And if you were trying to build a theory of biology by only looking at 100 organisms, or you were trying to build a theory of cyanometrics by only looking at 100 papers, you would have a rough time, right? So we really would like to scale this up. And so the idea is that you could take data that looks like this and make predictions that look like this. So here we have instructions per second per dollar, so this is computation again over time. And you have some historical data there, and then you have a forecast. And so we have a 95% confidence interval and a 50% confidence interval. And then you can, having built a model that ran up to 1980, with data available at 1980, have it forecast into the future and see how well would you have done at forecasting, which many people in this room have done things similarly with predicting things like paper citation counts or whatnot. And then you can evaluate how well you did for any of those future data points, such as through probability density. So just a few definitions. The object of interest here is a well-specified technology, such as a lithium-ion battery and its power, and then some well-specified performance dimension, so like watt-hours per kilogram. And the ground truth here about the technology existing is that it's for sale. For IARPA's purposes, this is what are interested in, and this avoids things like replication crises, right? It's that, okay, it was in this journal article, okay, but did it really exist? If it's for sale, we're pretty confident that it probably exists. And we're thinking on the time scale of about 1 new data point per year per technology. But the problem here is that we need scale, and so we would like thousands of technologies with at least 1 time series each, but you might have multiple time series about multiple performance dimensions across decades of history. So then you can start to make predictions that look like this. But we would love to improve on this, which is just trend extrapolation, and instead find relationships like this, where you see some technology with its performance increasing over time, and you can see its performance change as some percentage over time. That's the middle on the left. But then you have some other data set, like patents, right? You have some other thing that you hypothesize is going to be a predictor, and so you'll see that change over time. And then you see some correlation, right? Some lagged correlation that, okay, if we have more patenting in 1 year, then we tend to see an increase in the performance change of whatever this technology domain would be 4 years later. It's important to know, we don't know this. There is nothing more than small case studies that illustrate this. So if you see an increase in patenting in a given field today, we don't have any idea how much performance will increase at some later date. If at all, it might even be negative, right? We have no data that answers this question that I'm aware of. If anyone in the room is aware of it, please tell me. I keep hoping that I'm going to turn over a rock and find the thing that I'm looking for. But in the meantime, at IARPA, we're very keen on this question. So what you want to do is find relationships like this that then let you improve on making forecasts that, like this. So you beat this. So you beat just simple trend extrapolation, but instead you're finding predictors of technology development, which may be causes of technology development, which then might allow you to find levers that create better policies for technology development. So the steps that IARPA is currently going through is collecting and organizing bunches of historical technology data. Then we'll build an automated trend extrapolation tool. This is pretty simple. Wall Street's very good at doing just trend extrapolation, so there's not a lot of difficult science in that realm. And then we'll be funding teams of researchers to try to beat trend extrapolation. And I am totally agnostic as to what the predictors could be. And so this community has developed tons of understanding of a lot of the mechanisms happening inside of science and technology. So there's all sorts of great hypotheses in here about what could be relevant for predicting future technology development. And so the goal would be to have quantitative models that predict the performance of thousands of technologies. So that is a road that IARPA is going down right now. And we do this by funding researchers like yourself on aspects of this problem. Now that was all one sort of vision for technology, and I would really love it if this community and related communities would ask, what would be the analogous task for science? Which in my view is very difficult because with technology we have some clearly defined artifact, right? You say a battery, and it's got this much energy density. But for science, what we said is knowledge, and I had a slide that said models. And for that, to see that changing over time, you really need to dig into a paper and say, what is the model of the universe that it is espousing? And can we see those models change over time? Can we see the error bars within those models tighten over time? And that sort of thing. So I think that is a much bigger lift, but I hope it's the sort of thing that this community moves to in the future. So we at IARPA really want ideas from you. So I said my vision, but you are all the ones that are actually working on this day to day. And so we want ideas from you, and at IARPA we have these large flagship programs that have a lot of bureaucratic heft to them, but we also have a smaller funding mechanism called Seedlings. These are 9 to 12 month studies. You can submit any time. And so the mechanism is that you have an informal conversation with a program manager such as myself, and then you submit a proposal. The informal conversations could be two or three iterations, or it could be a dozen. But it's fairly low overhead in comparison to other forms of submissions. So that is the vision here at IARPA, and so this is a community that hasn't frequently worked with places like DARPA and IARPA, so I appreciate being here in order to tell you about who we are and how our interests align. So thank you very much.